In problem 1.15, we are given two solutions to the Schrodinger equation, denoted psi sub 1 and psi sub 2, and they both have the same potential, v of x, and we want to show that the time derivative of the integral from negative infinity to positive infinity of psi 1 conjugate multiplied by psi 2 dx is equal to 0. Now, if you remember earlier on, one of the things that we proved in this chapter was the preservation of normalization over time, where we said that given some function psi, we could sort of confirm that the time derivative with respect to time, or just the time derivative, I don't know why I put it in such a fancy way, but the time derivative of the integral from negative infinity to positive infinity of mag psi squared dx, which is the same thing as psi star times psi, must equal 0. And the reason why we sort of required this is because if we have a function, or if we have a constant a in front of this, in front of our wave function psi that normalizes it, we sort of required that this wave function would remain normalized over all of time. And in order to do that, one of the things we required was that the area underneath the curve had to sort of remain constant over time. The wave function could not evolve and gain or lose area over time, because otherwise sort of the integral from negative infinity to infinity, this part of our function would end up not equaling 1, and we can't allow that. So this is sort of analogous. The only difference here is that psi 1 and psi 2 are different wave functions, apparently. However, according to this proof that we are supposed to show, this evidently isn't supposed to matter in the long run. And apparently, as long as two wave functions have the same potential for a given scenario, they are effectively identical to each other and can be used in this proof that we did earlier on in the textbook. So let's sort of show that, and the actual proof for this is pretty much analogous to the proof that we did here early on in the textbook for this part, where we talked about the preservation of normalization. So if you want to go back and look at that, it's basically the same thing that we're going to go over. So let's just start right away, and we're going to do this in red. So let's take the derivative over time of our integral from negative infinity to positive infinity of psi 1 star times psi 2 dx. And first thing we're going to do is we're going to move our derivative into our integral. Then we start by using, evidently, the product rule to sort of do this derivative. So this becomes the integral from negative infinity to positive infinity of the partial of psi 1 star with respect to time multiplied by psi 2 added with psi 1 star multiplied by the partial of psi 2 with respect to time. And this whole thing is multiplied by dx to close off our integral. Now, sort of the next step that we did in the original proof was we converted this time derivatives into position derivatives by taking advantage of the Schrodinger equation. So let's do that as well. So we know, according to the Schrodinger equation, that the partial of psi 1 star with respect to time is going to equal negative I h bar over 2m times the second partial of psi 1 star with respect to x squared plus I times the potential v over h bar times psi 1 star again. And I'm not going to prove this. We sort of already did this earlier on, so you can just look back on the earlier video talking about the preservation of normalization. Now, for the other one, which let's write in dark purple, the partial of psi 2, which is not a complex conjugate with respect to time, is going to be equal to the same thing, but with all of our imaginary signs reversed. So positive I h bar over 2m this time instead of negative, times the second partial of psi 2 with respect to x squared, subtracted by I times our potential, again, v over h bar times psi 2. And so we can just plug these in, sort of. So let's do that right away. So this becomes the integral from negative infinity to positive infinity of, and first off, our partial of psi 1 star with respect to time. So let's sort of copy paste this over here. And I'm going to add bracket symbol right here. This is going to be multiplied by psi 2. Let's just make my window a little bit larger. Okay. Psi 2, and then we're going to add psi 1 star multiplied by the partial of psi 2 with respect to time, which is here in dark blue. And let's just sort of make our canvas a little bit bigger. There we go. And let's do this, bracket it off, and then everything by dx. And hopefully you see, first off, we have positive IV over h bar psi 1 star psi 2. And on this side, we have negative IV over h bar psi 1 star psi 2. So these two instantly cancel out. This becomes the integral from, and in fact we can actually, since there's only two terms left, we can move our RH bar of I h bar over 2m to the front. So this becomes I h bar over 2m times the integral from negative infinity to positive infinity of the partial, second partial of psi 1 star with respect to x squared multiplied by psi 2. And we're adding this to psi 1 star times the second partial of psi 2 with respect to x squared dx. And once again, sort of the requirement that we need to have, and sorry, apologies, this is supposed to be a negative at the front here, and the requirement we have is that this must equal 0. We must confirm that this equals 0 to solve this problem. So, from here, the process of solving this is pretty much exactly step-by-step identical to sort of the preservation of normalization that we worked on earlier on. If we sort of, I'm going to walk this out a little bit and do this fully, but by all means, if you already know this, there is nothing else to this problem, so feel free to just click off. But what we're going to do now is we're going to sort of force this to cancel out by enforcing integration by parts. So what we can do is let's refer to this as equation number 1, and let's refer to this as equation number 2. So first off, I'm going to say that I'm going to do an integration by parts on this first part of this integral on part 1, and we're going to say that u equals psi 2. And then I'm going to say that du is then therefore equal to the partial of psi 2 with respect to x dx. And evidently, since we're doing integration by parts, we have to define dv. Apologies for that, my phone just rang, so let's just start off right where we left off. So here in green we have we've assigned u to equal to psi 2, so du equals the partial of psi 2 with respect to x dx. dv is going to be equal to our second derivative with respect to x, which goes down to the first when we integrate it to v, and we do the exact opposite for purple in this second expression, where instead u here is going to be psi 1 star instead of psi 2 instead. Du goes down into a derivative, and then dv is going to be the second partial of psi 2 with respect to x squared instead of psi 1, so v goes into the first partial. And instantly, we can just plug this in, so this is going to be equal to, and we have the same I h bar over 2m on this side, and we're going to get, so we'll start off here, there's a negative at the front, we have to remember that, so the negative of, and then in green, it's going to be in parentheses, uv, so psi partial of psi 1 star with respect to x times psi 2, evaluated from negative infinity to positive infinity, minus integral of v du, so the integral with the same limits, negative infinity to positive infinity, of v du, so partial psi 1 star with respect to x times partial psi 2 with respect to x dx. And this is our green expression. And we're going to add the integration by parts in purple. So first off, uv, so psi 1 star times the partial of psi 2 with respect to x, evaluated from negative infinity to positive, whoops, that is a very ugly looking infinity, negative infinity to positive infinity, minus v du, so minus the integral, again, from negative infinity to positive infinity of partial psi 1 star with respect to x times partial psi 2 with respect to x dx. And we close this off with the bracket. So first off, hopefully you recognize that one of the things that is required in order for psi to be a valid wave function is that it has to go to 0 at positive and negative infinity, otherwise it would not be normalizable. We sort of went over this earlier on. So because of that, here we have psi 2 evaluated at positive and negative infinity, so this instantly just goes to 0. Same thing in purple, we have psi 1 star evaluated at positive and negative infinity. This also has to go to 0. So as a result, we have I h bar over 2m, and then in brackets, we're going to apply the negative now. So a negative and a negative makes a positive. So we just have positive of the integral from negative infinity to infinity. Let's just copy paste this. Have this expression, and then we are adding, or in this case, subtracting, because a positive and negative make a negative. So subtracted by, and we're going to do this same thing here, subtracted by this integral. And these two integrals are the exact same. Integrals from negative infinity to positive infinity of partial psi 1 star with respect to x times partial psi 2 star, or partial psi 2 with respect to x. So these two just instantly cancel out to 0, and as a result, this function equals 0, which is exactly what we wanted to prove in this problem in the first place. Therefore, we are done with this problem.